Hello everyone. Today I am going to discuss on feature scaling. It's a very crucial step of machine learning because many model needs feature scaling of their data before train the model. So actually many people know that feature scaling is simply just transform to in the data into the same scale in the same numbers range. So but here I going to discuss just under the hood, okay, and also are going to discuss why we actually do it from the perspective of uh, mathematics, geometry, and optimization. Let's have a look. So what is feature scaling? As I said, feature scaling is actually making all the columns have similar range of your data set. So imagine a data set containing age 18 to 60 and the salary is 20k to 200k. Okay, to a machine learning model, salary appears roughly 5,000 times larger than the age, right? It is just number 18, 20, 30, 50, 60. But here 20k, 30k, 40k, 100k, very large. Okay, so as the some machine learning algorithm use some distance calculation. Okay, so in that case, this high number actually affect the model. The model will actually bias to the high numbers. Not all the ML model use the this type of calculation where data feature scaling is needed. But some model use some calculation, distance calculation. Also, some model which actually use gradient descent to improve the model. So those models, ML algorithm, need to scale their data before training. So real life analogy is like when buying a house based on distance, 5 km versus 7 km, and price is like this, 5 lakh to 5 lakh and 50 sorry, 50 lakhs and 55 lakhs. Okay, so without killing the algorithm mathematically prioritize the price almost entirely ignoring the distance because this is very low number 5764, but price is very high. It will neglect the price, sorry, distance, but distance is a very crucial thing to decide the price of a mm, any house. Just think it geometrically. Without scaling, stage geometry. So if we plot our data in 2D space, but feature 1 is age and feature 2 is salary, the geometry becomes heavily distorted. And after scaling, uh, the now it will become normal. Okay, so any distance based calculation will be disproportionately skewed along the longer axis if we not scale our data set. For example, just let me show you. This is sample data set. This is age, salary. Okay, you can see it. Let me show you the how geometry looks like. Suppose we are not scaling. You can see age axis is very small, but salary axis is very high, right? But after scaling, it will looks like this. Now it looks balanced, right? So that's why scaling is very important. Yeah. So k nearest neighbor. Okay. Use the feature scaling, needs feature scaling because is use the distance. Suppose one person age is 20 and salary is 30K, and person B age is 50 and salary is 31K. So if we find the distance from between person A and person B, it will give 1000. But here you can see the age difference is 20 and 30 and 50, huge age gap, right? Around 30 years gap. But despite a messy 30 years gap, square to 900, the minor 1000 difference is in salary dominates the calculation. See, because we are squaring, if we square the 20 minus 50, 30 square, and 30,000 minus 31,000, but the gap of the salary is very low compared to age. But here you can see it give priority on the salary. This 1000 indicates the is prioritized on the salary, not the age, right? So that's why scaling is needed. If we scale the value to the same level, so it will equally prioritize all the features. I will show you in example. Obviously, it will affect the gradient descent optimization, as we have discussed previously that how we can calculate gradient descent. Okay, so if you can understand, if you watch our previous gradient descent tutorial, obviously you can understand why the scaling is needed. Right? Otherwise, it will this gradient descent curve will be zigzagging. Okay. There's several type of method to standardize or scale your data. One is standardization or Z-score. We all previously I already discussed. This is a formula is like x minus what? This is the mean. X minus mean divided by standard deviation. This is a formula of standardization. Z-score standardization. Z-score or standardization. Okay. So suppose it's example like age. Okay, all is an age. First, we have to find the mean. Mean average, right? And calculate the standard deviation is 7.07. And suppose we are normalizing the age 40. How? So x minus mean. So age is 40. Here x is a original value 40 minus mean get by standard deviation. It is 1.41. Now x become 1.41. Okay. Also other method like MinMax scaling. But before that, this is the mean and standard deviation plus 1. Okay. You can see mu becomes 0 if we find a mean and standard deviation. Okay, after scaling. And alternative scaling method, as I said, mean and max scaling. The formula is like actually transform data to fit perfectly within a specific bound, typically exactly from 0 and 1. Suppose you want to transform the value and fit perfectly within specific range like 0 to 1, you can use this normalization method. So x minus mean and max minus mean. For example, age is 30, range is 20 minus 40. Okay, this is the range. That means minimum is 20 and maximum is 40. So as per the equation, x minus mean 30 minus minimum value divided by 40 minus 20. What is the max? So 0.5. So for S30, after scaling, it becomes 0.5. So this is based for bounded data when distribution is not Gaussian. It's for bounded only. Now it is robust scaling. Used specifically when significant outliers exist. So that means if the data have outlier, certain big values are present. So use specifically when significant outlier exists in the dataset, which would otherwise wrap the mean and standard deviation. Instead of mean, it uses the median. Obviously, but if the big outlier is present, it will move the mean towards the outlier, right? It will give you the wrong value. We already discussed previous lecture. So in that case, we can use the median. So instead of mean, we should use median. So in this, instead of standard deviation, it uses the IQR, interquartile range. Actually, it's divided the data set into sorted data set into 4 part, as we discussed before: 25%, 50%, 25%, and rest of it. Right? So when the data set has outlier, we should use this robust scaling. So if you want to scale your data uh, between 0 and 1, you can use max, min, max. Otherwise, you can use Z score. So now just have a look what ML algorithm use this scaling. Okay, so k nearest neighbor, KNN, Yeah, is because of scaling, because you is use the distance calculation. Okay, support vector machines SVM you also need because relies on the geometric distance between support vectors. Neural network or logistic regression also need scaling because smooth cost surface for gradient descent because is use the gradient descent. Principal component analysis or PCA, yes, needed. And components are determined by maximizing variance. That's why. Descent is not needed because split nodes based on the single feature condition. Random forest or exhibits also not needed. So this is a table. This some basic ML algorithm mentioned and where which either need require the scaling of the data before training and not needed the scaling. Okay, so now for the predicting house price in the last discussion texture we have shown house prediction. The raw data we are predicting house price using KNN based on area, right, and bedrooms. The method flow is when calculating Euclidean distance, this area square plus square root over the area completely dominates as I already shown you. As a result, KNN model effectively ignores the number of bedrooms, treating the 5,000 square foot 2-bedroom house and adding it to the 5,000 square foot 5-bedroom house. Because of the score of the if we use uh, data without scaling, it will predict on the area, not the number of bedroom. So solution is after MinMax scaling, both area and bedroom are transferred into values from 0 to 1. Now all are in the same range. Now you can effectively calculate the distance because now all the features contribute fairly as are in the same range. So feature scaling is the process of transforming feature into a comparable numerical range to prevent large scale features from dominating smaller scale features. It improves distance based algorithm, accelerates gradient descent coverage, and ensures fair feature contribution in ML models. So feature scaling is not about altering your underlying data. It's about making all features speak with equal volume. Without scaling, salary shouts, age whispers. With scaling, every feature gets an equal chance to influence the model. Okay. So now move to the code. This example is a small code script just how after transforming data it looks. Okay. These are age and salary data set. For age 20 getting 30K, 25, 50K, this is this, so on. As I shown before as well, like this 20, 30, this type of this is data set, sample data set. Okay, more value also present. Only 3 values present here, but here 2, 3, 4, 5 value present. Okay, 5 row present. So now here we are using the standard scalar class of the scikit-learn model. Now we are creating the object scalar object of the standard scalar class and we are using the feed transform. Feed transform is a do two things. First, calculate the mean and standard deviation, and then transform the values, because these two things needed to transform the values, right? For the z for the z square, z score, okay? For the z score, this formula. And now scale data is scaled and printing the scale data. And also here you are showing the, if we transform the same data using transformer, how it looks. It will give the same output, because using the feed transform already calculate the mean and standard deviation and scale the data. So transform, you will use the calculated mean and standard deviation, which is generated using the feed transform model. It will give the same output. This is the data set. Now after transformation, first transformation is gives this data set, the data, and second transformation give this. You can see all values are same, right? So because we are using same mean and standard deviation and same equation, so obviously it will give the same value, right? Now let's discuss about the feed transform and feed transform. Okay, so again we are using the same library, scikit-learn, and standard scalar class is a age data set only. Here we have not taken the salary, only the scale to show the how we feed feed transform works. Scale feed print this scatter mean and standard deviation. You see, mean is 40 and standard deviation 40 something. Okay, as I said, feed actually calculating mean and standard deviation, and transform applies a learned parameter. It is actually transforming the data into scaled data using Z score formula. For Z score formula, we need a mean and standard deviation, and transform function use these two values, right? So first we have to use the feed, then we can use transform, right? And you can see this is, it returns the value. And what is feed transform? Actually, it's a combination of feed and transform. It do the both. Don't need to use feed separately. Same output it will give. The same concept. Just these are splitted, feed and transform. Here merge into one function. Only this is the difference. Basically, when you going to scale your training data set, you should use feed transform. And when you going to test it, your model, you should transform the data set using transform, because feed transform or feed or transform, feed already calculate the standard deviation mean. And using same mean and standard deviation, we should uh, transform your training data set as well. Okay, so this is the logic. Fit is learn, transform is apply, and fit transform is learn plus apply. So I will share the Git repo, where actually it will contain this code, these two files. Okay. So thank you for watching this tutorial.